Why do you live in a 3D world? I mean, you get exactly 3 ways to point: left, right, up, down, forward, back. Not 2, not 4, and definitely not 17. It sounds like a simple, almost childish question, but it's the most important question about your existence that you've probably never asked. Because the answer is the only thing stopping reality from completely falling apart. What if I told you that our universe passed the cosmic stress test that countless others failed? Today, we're not just going to talk about other dimensions. We're going to visit them. We're going to change the rules of reality, and watch what happens to your life support systems, to the planet beneath your feet, and to the atoms inside your body. Welcome to the ultimate audit of the universe. The one that reveals why 3 is the magic number for life itself. Alright, let's run the first thought experiment. We're going to build a universe from scratch, and we get to choose the number of spatial dimensions. What's the first thing we need for a universe to be interesting, to support something like us? We need things to not fall apart. We need stability. So let's start with a flat, 2-dimensional world. Flatland. Everything exists on a single sheet of paper. What breaks? Well, you do. Instantly. Think about your circulatory system. Your heart pumps blood through a complex network of arteries and veins. It's a 3D marvel of plumbing where vessels can cross over and under each other. In 2D, nothing can cross. Ever. To get from your heart to your brain, a blood vessel can't go over another one. It would have to go through it, or create a traffic jam from hell. Your entire biology would be a hopelessly clogged maze. Knots, the simple act of tying a rope, couldn't hold. DNA couldn't coil. The complexity required to build a single cell is just gone. 2D fails the biology test. Spectacularly. Okay, so more must be better, right? Let's crank the dial up to 4 spatial dimensions. An extra direction to move in. Sounds like freedom. So you place your coffee mug on your desk. But now, it doesn't just have front-back, left-right to tip over. It has a whole new axis of instability. It can fall over in infinitely more ways. Balance becomes a knife's edge. The delicate structures in your inner ear that give you balance would be overwhelmed. Every skyscraper, every bridge, every bone in your body would be fighting gravity from a new, unexpected direction. Structures become fundamentally fragile. And what about that planet you're on? In a 4D universe, its orbit around the sun becomes a terrifying gamble. It either spirals away into the frozen abyss or plunges directly into its star. Why? Because gravity's grip gets weaker, much faster. The perfect balance is lost. So here is our official audit checklist, the criteria for a universe that can host minds and build memories. 1. Do structures stay stable? 2. Does motion stay predictable? 3. Can signals travel without turning to mush? And 4. Can complexity build on itself over time, or does it just collapse? Let's dive into the physics of why 3 dimensions passes with flying colors. First up, we have to understand how fundamental forces, like gravity and electromagnetism, fill space. Physicists have a beautiful tool for this called Gauss's law. But forget the name, here's the idea: imagine a single point, like our sun, radiating gravity in all directions. Think of its influence as a fixed amount of light shining from a bulb. In our 3D world, that light spreads out over the surface of an expanding sphere. As the sphere gets bigger, the same amount of light has to cover a much larger area. So, the light gets dimmer. The area of a sphere grows as the distance squared. So the light intensity, or the force of gravity, gets weaker as 1 over the distance squared. That is the famous inverse square law. It's not an accident, it's the geometry of 3 dimensions talking. Now, why is this so important? Because this inverse square law is the secret recipe for stable orbits. It creates a perfect cosmic harmony. It's strong enough to keep Earth from flying away, but it weakens just fast enough that we don't spiral into the sun. It allows for beautiful, closed ellipses, orbits that repeat. Year after year. Eon after eon. This cosmic rhythm is the bedrock of life. It gives us predictable seasons to plant crops, a stable climate to evolve in, and a calendar to mark our memories. So what happens when we break it? Let's go back to our other universes. In a 2D world, that influence spreads out over a circle, not a sphere. A circle's circumference grows with distance, not distance squared. So gravity weakens much more slowly. An orbiting planet would feel a pull that's too sticky. The balance is off. The dance becomes clumsy. Now let's try 4D. That influence spreads out over the surface of a 4-dimensional hypersphere. The surface area here grows with distance cubed. Gravity gets weak fast. too fast. Any tiny nudge from another planet, a passing asteroid, would be catastrophic. The orbit wouldn't just wobble, it would unravel like a frayed rope. Planetary systems would become chaotic games of cosmic pinball, with planets being ejected into deep space or swallowed by their stars constantly. Without the predictable rhythm that only a 3D inverse square law provides, the universe loses the metronome required to build anything lasting. Okay, so gravity works perfectly in 3D. The big stuff is stable. But what about the really, really small stuff? What about the atoms that make you? For that, we need to look at the quantum rulebook, the Schrödinger equation. This equation describes how electrons behave around the nucleus of an atom. They don't orbit like planets. They exist in clouds of probability called orbitals or bound states. Think of a guitar string. When you pluck it, it can only vibrate at specific frequencies to produce a clean note. Any other vibration just dies out. Those clean notes are standing waves. A bound state is the electron's version of a standing wave. It's a stable hum of energy where the electron can exist indefinitely. The collection of all possible stable notes an atom can play is what gives us the periodic table. It's the foundation of all chemistry. And guess what? This entire architecture is exquisitely sensitive to the number of dimensions. In 3 dimensions, the electric force between the positive nucleus and the negative electron is, you guessed it, an inverse square law. Just like gravity. This specific relationship creates a beautiful, cascading ladder of stable energy levels. You get the familiar shells, s, p, d, f orbitals, that allow for the incredible richness of chemistry. Atoms can link up, fold, and build the complex 3D molecular scaffolding of life, like proteins and DNA. Now let's run our stress test. Slide down to 2 dimensions. The force law changes. The quantum balancing act changes. You can still trap an electron, but the ladder of stable states becomes much shorter and simpler. Chemistry flattens out, literally. The potential for complex, twisted, folded molecules, the kind you need for life, is almost entirely gone. Okay, let's jump up to 4 or more dimensions. This is where it gets really weird. The force law weakens faster, just like gravity did. This makes the pull of the nucleus on the innermost electrons too strong, and the pull on the outer electrons too weak. The result? Quantum chaos. The electron can actually spiral into the nucleus, annihilating the atom. Stable bound states, those clean notes on the guitar string, either cease to exist or become so precarious that atoms can't form lasting bonds. Without the specific quantum landscape of 3D, the periodic table dissolves. Chemistry as we know it is impossible. If atoms can hold their own stories together, biology can't ever begin to write with them. So we have stable planets and stable atoms. But for anything interesting to happen, they need to be able to talk to each other. Information needs to travel. And that brings us to waves. Light is a wave. Sound is a wave. Gravity travels in waves. A wave is just a disturbance, a message traveling through space. Here's something incredible about 3 dimensions. Waves are crisp. They are clean. Think about clapping your hands. The sound travels outward as a sharp pulse inside an expanding sphere. Someone a block away hears the clap, and then it's over. The cause, the clap, has a clear, localized effect in time. The message arrives, delivers its payload, and then gets out of the way. This property, called Huygens principle, is crucial for causality. It lets the universe have a clean conversation, where cause and effect are neatly ordered. You hear the thunder after you see the lightning. This clean signaling breaks down in other dimensions. In a 2D world, if you drop a pebble in a pond, you see the ripples spread out. But notice something. After the main ripple passes, the water keeps sloshing around. The tail of the wave lingers. The message gets smeared out in time. In higher even-numbered dimensions, it's even worse. A clap wouldn't be a sharp crack. It would be a crack followed by a long, echoing rumble, even with no walls around. Every event would bleed into every future event. Imagine trying to have a conversation where every word everyone has ever spoken is still echoing in the room. The universe would be a cacophony of overlapping echoes, not a clear conversation. Information would blur. Cause and effect would become a confusing mess. 3 is the sweet spot for clean communication. Let's push this to the biggest scales imaginable. We need to talk about Einstein's general relativity. Gravity isn't just a force, it's the curvature of space-time. Matter tells space how to curve, and curved space tells matter how to move. In our familiar 3 space plus 1 time dimensions, this theory gives us the universe we know. It gives us stable black holes, cosmic endpoints where collapse is tidy and final. They have a clear boundary, an event horizon. Simple. Clean. But in higher dimensions, new monsters appear. The zoo of cosmic objects gets bizarre and unstable. Instead of neat spherical black holes, you can get black strings or black brains, horizons that are stretched out across vast distances. And these objects are often violently unstable. They can sag under their own gravity, wrinkle, and snap in half, releasing catastrophic blasts of energy in unfamiliar ways. The quiet reliability of spacetime itself is threatened. Go down to fewer than 3 dimensions, and gravity becomes toothless. In a 2+1 dimensional universe, there are no gravitational waves at all. Stars don't radiate gravitational energy. The cosmos becomes quiet and strangely static. Our dynamic, evolving cosmic architecture of galaxies, stars, and black holes leans hard on the number 3. But hold on. Does this mean more dimensions are impossible? Not necessarily. Our best theories, like string theory, actually require more dimensions to work, 10 or 11 in total. So where are they? The leading idea is that they are curled up, compactified, so ridiculously small that we can't see them. Imagine a garden hose stretched across a canyon. From a helicopter far away, it just looks like a one-dimensional line. But for a tiny ant walking on it, there's a second dimension, the path that goes around the hose. For decades, we've been looking for these hidden aisles in reality. Physicists conduct precision tests of gravity, looking for tiny deviations from the inverse square law at sub-millimeter scales. If gravity could leak into these tiny extra dimensions, it would get weaker than expected up close. Particle colliders like the LHC smash particles together at incredible energies, hoping to see some energy disappear as it escapes into another dimension. So far? Nothing. Every experiment has returned a quiet, simple answer. If extra dimensions are there, they are incredibly small, tightly curved, and very, very shy. For all practical purposes in our macroscopic world, we live in 3. Now we're at the bleeding edge, where physics starts to sound like philosophy. What if dimensionality isn't a fixed, fundamental property of the universe at all? What if it's emergent? Some theories of quantum gravity talk about spectral dimension. Forget the fancy name. Here's the concept: put a random walker, a tiny drunken ant, somewhere in spacetime and see how it explores. The faster the ant finds new territory, the higher the dimension it perceives. At our human scales, it explores just like it would in a 3D world. But some of these theories predict that at the tiniest, subatomic scales, the Planck scale, the universe might behave as if it's 2D. Dimensionality might actually flow and change with scale. Here's an even wilder idea. What if space itself isn't the stage, but a tapestry? A tapestry woven from the invisible threads of quantum entanglement. In this view, what we call distance and location is really a measure of how strongly 2 tiny bits of information are correlated. Dimensionality is just a pattern of the weave, how many threads connect to any given point. It's a radical shift. Space isn't the box information lives in. Space is the information. And from that perspective, maybe our universe simply settled into the most stable, efficient pattern for storing and processing information. And that pattern has 3 dimensions. This brings us back to our cosmic audit. We subjected different universes to a brutal stress test. We asked, which dimensionality allows for stable atoms? For predictable orbits? For clean signals? For complexity that can build on itself without collapsing? 2 dimensions is too restrictive. It's a prison. 4 and above are too wild, too chaotic. They are mansions with too many doors, where everything gets lost or breaks. 3 dimensions. 3 is the sweet spot. It's the perfect balance between rigidity and freedom. It's the minimum architecture required for a universe that can form memories. So the next time you pour a glass of water, tie your shoes, or look up at the moon, remember that simple act is a testament to the profound stability of 3 dimensions. Your body is a cathedral of 3D engineering, from the folding of proteins to the weaving of neurons. Our very thoughts, our language built on spatial metaphors, our ability to remember yesterday and plan for tomorrow. It all depends on living in a cosmos where information doesn't leak away into chaos or get locked into simplicity. Perhaps the universe doesn't prioritize simplicity or elegance. Perhaps its first priority is simply this: creating a place where a story can be told and remembered. A place where things can matter, because they last. And it turns out, a universe with 3 large spatial dimensions is the best stage for a story ever built. We are not done looking. We'll keep searching for hints of those tiny, hidden dimensions. But for now, 3 is our home. So here is my question for you today. If you could have access to one extra tiny, curled up dimension in your daily life, what would you use it for? The ultimate secret hiding spot? A shortcut through traffic? Drop your most creative idea down in the comments. I'm genuinely curious what you'll come up with. And for more daily audits of reality like this one, make sure you're subscribed with notifications on. On the end screen right now is another cosmic puzzle the algorithm has chosen just for you. Click it, and keep exploring. Thanks for auditing the universe with us today.